All right. Thanks very much, John, for the introduction, and thank you to John and Thorsten for having me. Uh, so broadly speaking, my group at UT Austin, we're a theory group that thinks a lot about what really makes some systems intrinsically easier or harder to predict, and especially to forecast. And that's the kind of question where if you go to a physics conference or a SciEM conference or something, the folks there will pretty happily tell you that this is a problem that we kind of already know the answer to. Right, so traditionally speaking, in applied math, we think of systems as having sort of predictability as some intrinsic property of what makes them something that we're able to gather enough information to forecast or not. So usually when we think about predictability in sort of a physics setting, we usually talk about something about whether the underlying system has something like a positive Lyapunov exponent, which means that's chaotic, or whether it has some invariant property like a high Reynolds number. So in other words, usually when we talk about whether something's predictable or not in physics, it's usually a well-defined mathematical property of the system. The problem that I have with that idea is that if you go to really any other conference, often people don't really care about whether their underlying system is actually predictable or not. So I go to a lot of biology conferences, and at a conference like that, whether or not the underlying dynamical system has a positive Lyapunov exponent is not necessarily something that people are all that interested in, because usually our ability to predict a system like a biological system is really limited by whether or not we even can measure the variables we need to build a predictive model. Right, so if I'm someone who's trying to model some gene regulatory network, I might have something like 3 fluorescent readouts in a 20 regulatory motif system. And so in a case like that, whether or not the underlying system has some differential equation that has a positive Lyapunov exponent is really far from the problem I'm studying, because really I'm limited by my ability to extract the information from the system I need to build a model. So broadly speaking, I think that there's kind of a dichotomy in the forecasting community between this idea of predictability as some intrinsic invariant property of some underlying dynamical system, and predictability being something information limited or something bounded by some observable property of the system. Okay, so this idea of sort of an intrinsic versus observable predictability is how I think of this problem, but it turns out that if you go a little bit deeper into the dynamical systems literature, there's actually kind of a connection between these two ideas of information-limited prediction versus invariant property-limited prediction. And the idea here is that on some level, if I have some really chaotic or complex system, I can think about the process of watching that system unfold over time as something analogous to sort of sampling a really complicated probability distribution. So if I go through a lot of trouble to build some really complicated turbulence simulation, I get all my variables right, I set up my supercomputer, as I sit there and observe new states from that simulation, on some level I'm learning something new about what is possible for that underlying system of equations. Right, so I might be able to use tricks from statistical physics to say something very general about where I typically expect the system to go, so I can maybe make sort of broad statistical claims, but I don't actually know whether some pattern I see in my simulation lies on or off that system's attractor until I've actually seen the system pass through it. So in other words, as I sit there and I watch some deterministic complex system unfold over time, on some level I can think of myself as gaining information about that system's underlying attractor. So there's a positive rate of information gain associated with watching a deterministic system evolve. And it turns out that you can actually make this a little bit more precise. So it turns out that any chaotic system, so that's any system that has a positive Lyapunov exponent, it has an information production rate that's bounded from below by its Lyapunov exponents. So what that means in English is that effectively, the more chaotic a system is, the higher the rate at which I gain information about what that system can do. So there's a way to associate the idea of information gain with the idea of whether or not a system is predictable or not. So this is an idea that I think is very compelling. This is just that even if I have a completely deterministic system, it somehow might admit a probabilistic description where I can think about the process of watching the system as generating samples from the system. And this one idea, the idea that deterministic systems are probabilistic and we can think about them probabilistically when we build forecast models, this is more or less the core of what my group does when we think about how to build predictive models. Okay, so I'm going to talk about two ideas that broadly fall under this category of sort of probabilistic prediction. So first I'm going to talk about how you can use this probabilistic view of prediction to really try to talk very generally about the space of possible chaotic systems and what makes certain kinds of systems intrinsically easier or harder to predict. And then I'm going to circle back and talk about how we can use these ideas to try to quantify what makes a forecast model good or not. So a little bit more on the practical side. Okay, so a couple of years ago, as something like, I guess, a lockdown hobby or something, I tried to go through the literature and write down basically every system that I could find that someone has published that exhibits low-dimensional chaotic dynamics. So this includes a lot of systems that are very popular with mathematicians, things like the Lorentz attractor, which we saw in John's talk, as well as a bunch of other systems in that, from that time period. But it also includes a bunch of systems that are more or less drawn from very specific domains. So if you go into climate science, there's a lot of very low-dimensional chaotic systems. In neuroscience, it's very common to write down sort of toy models that exhibit chaos. And the point of doing this is that when we talk about chaos, we often talk about it in sort of very cherry-picked examples. And I wanted to see if I could do something a little bit more systematic to understand what the space of possible chaotic systems might look like. So I went through the literature. I dug out every system I could that I could successfully re-implement. It turned out there's about 135 that we're able to get working. And then over time, since I've released it, people have gradually added systems to this data set. So this more or less represents a data set of every published example I can find of a low-dimensional chaotic system. And my goal in doing this was to maybe look comparatively across these different systems and say something about what is common and different across all these systems that makes them intrinsically easier or harder to predict. So what I've done is all of these on some level are just differential equations in some list somewhere. And we've tried to go through and standardize them so that various timescales and such are aligned so we can really compare them on equal footing. And when we have that list, we can start to ask questions about how the properties of these systems vary systematically. So for example, every single one of these systems that people have published in the past, it has a different Lyapunov exponent. So that's one number that you could use to differentiate different systems in this collection from each other. But it turns out if you dig into the nonlinear dynamics literature, there's actually hundreds of other invariant properties that you can use to compare to chaotic systems. So we went through and for every single one of these 135 systems, we calculated, it turns out, several hundred different invariant properties. So Lyapunov exponents, fractal dimensions, various spectral properties. So instead of thinking about these systems that have been published before as just like a list of equations, you can really think about each one of these systems as a vector in a very high-dimensional space of invariant properties that might differentiate that system from all the others. So we're going from a list of equations to something like a space or a vector space of invariant properties that differentiate these systems from one another. The reason that you might want to do that is that you can then take those vectors and try to visualize what the space of these known chaotic systems looks like. So what I'm going to do here is for every single one of these different systems, I have a vector in this very high-dimensional space of possible invariant properties, and we're just going to try to look at what that vector space looks like. Okay, so what I'm doing here is every point on this plot is a different one of these 135 systems. It exists in this high-dimensional space of invariant properties. I don't know a priori how to visualize a 700-dimensional vector space, so what we're doing is we're projecting that 700-dimensional space down to 2 dimensions here. And we're using a projection method that tries to preserve the nearest neighbors, so the neighbors of each point should be close to what they are in the original vector space. And the reason that we do that is that you can threaten to maybe talk about what the space of different chaotic systems looks like here. So for example, you start to see relationships among systems that aren't obvious just from looking at the original differential equations. And there's a lot of things that kind of pop out here. There's a little bit of historical contingency. So for example, in the 1960s, Lorentz publishes his original paper, and there's a lot of papers that come out after that that are more or less very small modifications of his equations. And those actually end up clustering together in this vector space of different invariant properties. So you can almost sort of see the sort of sociological progress there, where a lot of very similar systems were published around the same time. But what's cool is that this pops out in this purely unsupervised way where we're just comparing the systems by their intrinsic properties. But what's cool about having this space is you start to notice things that weren't so obvious before. So if you dig into the space of sort of chaotic differential equations, there's a lot of models that are more or less fast-slow oscillators. There's a lot of neuroscience models, a lot of sort of climate models that have sort of 2 characteristic timescales. And surprisingly enough, a lot of those end up clustering together when you just look at their invariant properties. So you start to actually take the fact that there's this very sort of specific list of systems that people have published, and you start to see where the sort of similarities in structure across all these differential equations pops up. So this is something we were very excited about because it meant that maybe we might be able to leverage the space of sort of what people have studied before in chaotic systems to feel out the kinds of dynamics there are, as well as maybe the kinds of dynamics that are missing. Okay, so I have this plot. It's more or less informed by what people have decided to study in the past. So the thing that people always ask me is what goes in the dark spots on this map, right? What are the regions where there are no systems that, to our knowledge, have been published before? So one thing that we spend a lot of time doing is trying to use methods to take this space of different differential equations and use it to extract new kinds of dynamics. So there's a couple of ways that you can do that. The one that is probably the most obvious is that each one of these is a differential equation. It has a bunch of parameters that characterize it. So you could always take one of these differential equations, make some small sort of epsilon change to it, repeat this entire pipeline, and just find where that new point goes. And it turns out if you do that at every single one of these points, you can always explore sort of a very small region around that point that corresponds to very, very small perturbations of its parameter values. And the reason this works is because everything I'm doing is not invertible, but it is smooth. And so any small change in the parameters ends up producing a very small change in embedding space. It turns out that if you try to do that with these systems, you usually don't get very far. So if I change a parameter of one of these systems, I get slightly different dynamics. At some point, I end up just having a bifurcation and my dynamics goes away. So you actually end up like a very hard convex shard around each one of these points that's just defined by its nearest parameter perturbations. So if you want to search a little bit more globally, then you have to get a little bit more creative, especially given that this is a non-invertible operation where you go from equation to trajectory to some point in some embedding space. So to do that, we've been using a bunch of tricks for searching non-invertible spaces, and we've gotten moderate success using genetic algorithms, which is a very sort of naive approach where you recombine terms of differential equations. And what's cool about that is you start to see structure pop out, where very gradually, with very inefficient searching, you can gradually discover new equations and start to fill in where you have proper sort of density in the space of possible chaotic dynamical systems. So this is something we thought was interesting because we thought that maybe it would tell us something about whether there's certain kinds of chaotic dynamics that are forbidden, whether there's some structure in this space that maybe hasn't been appreciated before. But it's also something that we think is interesting because it also allows us to learn something about just practical time series problems, even divorced from this sort of chaotic dynamical systems context. So one of the ideas with chaotic systems that I always found very interesting is this idea that because you observe them and you generate information as you sit there and watching them, you're always sort of gaining new information about that underlying attractor. And so we can actually use that idea to leverage the fact that we have this space of systems to effectively build surrogate data sets based around this space of dynamical systems. So a lot of what our group has been doing, especially the past couple of years, has been training very large models, leveraging the fact that because these chaotic systems are generative, you can always gain more points in the attractor from them, that allows you to sort of generate data that allows you to train larger models than you otherwise might be able to. So one of the things that we sometimes do is we take very small time series problems. A lot of biology problems involve very small data sets that aren't really appropriate for fitting large models. You can extract all of these different invariant properties, Lyapunov exponents, et cetera, et cetera. You can then embed them in the same space with the dynamical systems. You can then sample nearby systems, generate arbitrarily long data sets that are somehow matched to the properties of that original time series, and then use those sort of surrogate data sets to train your really large model. And it turns out that that works surprisingly well, where you can train a very large model, like an autoencoder on the big data set, and then just use that as some sort of feature extractor for your smaller time series problem. So in other words, you can leverage the fact that chaotic systems sort of continuously produce information. You can pull very long trajectories out of them to train large models. Even if you're not someone who a priori is that interested in chaos itself, you can use this property of it to augment your data set. So this is our space of chaotic systems, and it sort of is us threatening to talk maybe more broadly about the space of chaos. And one of the big things that results from this is this idea that because these models are generative, or the idea that you can think of chaotic systems as generating new information, you can leverage that connection to sort of create larger data sets than you otherwise might be able to. So the fact that we have all these different chaotic systems motivated us to try to take this data set and maybe try to think a little bit systematically about whether we could use this data set to probe different kinds of forecasting models. So now what we're going to do is we're going to take the sort of space we've constructed, which has all these different chaotic systems, and we're going to use it to construct a test to see whether this space tells us something about predictability. Okay. So I have this space of 135 systems. You can think of each of these as just a set of equations that we can generate very large amounts of data from. So for every single one of these different equations, we're going to do a very large-scale benchmark experiment. And the idea here is that for every one of these systems, we're going to train a whole bunch of different forecast models on trajectories from that system, and we're going to compare how different forecast models do on different dynamical systems. In our benchmark, we tried to be pretty general regarding the kinds of forecast models that we tested. So we have a bunch of more or less classical methods, linear methods, autoregressive methods that have been around for a very long time. We tried to test a few of these physics-based methods that there's been a lot of excitement about the past couple of years. So we have models like reservoir computers, which were used in the paper that John talked about earlier, which are effectively untrained linear models that have some inductive bias for chaotic systems, or are thought to. And then we also did things like neural ODEs, which also fall under this sort of physics-based category. But then in addition to sort of these physics-based models, we also try to include a couple of just truly large, low inductive bias models. So a lot of forecasting competitions the past couple of years have been won by variants of transformers, as well as various other kinds of architectures. In one architecture I'm going to highlight, because it's going to come up later, is that a lot of sort of purely time series forecasting competitions the past few years have been won by hierarchical models. So these are models that basically predict one time scale in a time series, then train another model that predicts the residual of that prediction, and they sort of build a forecast one time scale at a time. And these models, it's called N-beats, are very popular in a lot of sort of practical forecasting contexts. So when we designed this benchmark, we tried to have sort of a mix of different kinds of models: classical, physics-based, and purely sort of machine learning methods. And we wanted to see whether different kinds of models interacted better with these different chaotic systems, and really doing this sort of at scale across these 135 different systems. And I'll mention that when you do a benchmark this sort of with this many different models, you have to think a lot about how you control for parameter size, for the number of hyperparameters and stuff. And so we tried to be pretty fair when we compared the models regarding how much we tuned each model, just to make sure that we weren't giving too much of an advantage to the models with more hyperparameters. Okay, so we have these 135 systems, and for every single one of them, we're going to train a whole bunch of different forecast models. Okay, so when we do that, the first thing that pops out, which wasn't that surprising to us, is that it turns out that a lot of the larger models do truly do better on this problem. So it turned out that a lot of the largest forecast models, they're easily able to get beyond 1 Lyapunov time, which is the characteristic time scale that you expect to be able to predict a chaotic system. But what's interesting about this is that this is pretty systematic across these 135 different systems. So it's not like they're just good at predicting one or another. Generally, the models that are good at predicting the Lorentz attractor are also good at predicting these low-dimensional climate models, et cetera, et cetera. So these large models that have that do better at forecasting are pretty systematic, regardless of the underlying sort of structure of the attractor. So that was one thing that popped out. The other thing that popped out that was a bit surprising to us is that generally the models that are good at short-term forecasting are also the models that are good at long-term forecasting. So in other words, a model that does a very good job predicting just the next couple of time points in a time series also turns out to be the same model that does a very good job capturing the shape of the entire attractor. Suggested to us is sort of that there's a bit of contingency in forecasting, where if you're trying to build a model, you really have to get the first few time points right to even capture the structure of the whole underlying system. So that was the first thing that popped out, is this idea that larger models generically seem to do better on this problem. But one thing that really stood out to us is the fact that the larger models, their scale even compensated for the fact that they didn't have the same sort of inductive biases as things like reservoir computers and other things that have been designed for this task. So this suggested to us that maybe there's some intrinsic advantage of having scale, even on a time series task that really is a dynamical systems problem. Okay, and I'll highlight that on a couple of systems, like for example the Mackey-Glass equations, which is what I'm showing on the left here, you're actually able to get up to 5 to 6 Lyapunov times. So some of these forecast models really do represent progress over what was even possible a decade ago. Okay, so we have all these large models. They seem to do pretty well. So the first thing we were trying to figure out is whether that was that surprising, right? Whether that is interesting at all that these large models are very good at predicting these chaotic systems. And the reason that we were a bit skeptical that there was anything further going on here is because a priori we expect there to be sort of an intrinsic house advantage that comes from having a large forecast model. So even if you aren't that interested in the details of how an LSTM works or how a transformer works, there's some pocket intuition you might have that a larger model will do better at forecasting, because on some level, if you have a large model, it's always able to represent the dynamical system in a space where the dynamics look more linear. So this is an idea that I think is it's been trendy the past 7 years or so, but it's the idea that if I have some nonlinear system that lives in something like 3 dimensions, I can always make those dynamics look more linear if I lift it to more dimensions than are strictly necessary to represent the flow. So if I have something like a 3-dimensional system, if I perform some lifting transformation on the dynamics where I lift it to 10 or 30 dimensions, I might expect the dynamics to somehow act more linear in more dimensions. So this idea in dynamics is sometimes called Koopman operator theory, but there's similar ideas that pop up in ML theory. The idea there is that if I can somehow lift a system to a higher dimensional space, in that higher dimensional space, it might be closer to a linear flow, and linear flows are a priori easier to predict. So we had this sort of pocket intuition that these large models, regardless of their architectural details, all the choices that went into designing them, the fact that they have all these free parameters inside them, and the fact that they can take a long context, they can take many time points, means that internally they're able to construct higher dimensional representations just right off the bat. So we had this sort of loose intuition that scale alone gets you an advantage of forecasting before you get to any of the details of the models themselves, just because they can conceive of the data in a higher dimensional space. So this suggested to us that maybe we shouldn't be that surprised because there's sort of a house effect with large models that you don't get from these smaller, sort of more domain restricted models that people use for forecasting. So we wanted to take that idea a little bit further by seeing how far we could push this idea that raw scale can get you an advantage in forecasting. And the idea here comes from the sort of past couple of years where I think I'm frozen. All right. Cool. Yeah, thanks. Okay, so the idea is kind of simple. So normally when we talk about forecasting, we have sort of a very classical idea of it, where if I think about a classical forecast model, I have some long time series that's drawn from some underlying system. In my case, it's something like the Lorentz attractor, some differential equation, but it could be something like a stock time series or weather time series, depending on the application. So a classical forecast model usually involves taking some long time series and training a model that effectively performs regression, where it takes some number of past time points, we'll call that the context, and it tries to predict, let's say, just the next time point, and you can build a longer prediction autoregressively. So a lot of classical forecasting models have this idea that if you build a forecast model, you're training on a bunch of time series from one system, and then when you test it on different time series that are drawn from the same underlying distribution or the same underlying system. So in my case, I train a model on the Lorentz attractor, and then I test it on some new trajectory from the same underlying differential equations. And if you think about it, this is effectively an easier task than it could be, because on some level, you're assuming that your test data is drawn from the same underlying distribution as your training data. It might be a different data set, but the actual distribution is drawn from the same invariant properties should be matched across the two problems. But a lot of work the past 5 to 6 years has really focused on this idea that you don't necessarily even have to have this assumption that your test data is drawn from the same distribution as your training data. Right, so the whole idea of this whole foundation model paradigm that's very popular these days is that if you train a model on a whole bunch of data and it's a sufficiently scalable model, it might be possible to generalize to out of distribution test data sets. So in language models, this involves training on every piece of language in the book and then testing on new prompts that the system hasn't seen before. In a time series context, this consists of models where someone has trained one large model on a whole bunch of different time series from a whole bunch of different domains, and then they test on time series that it's never seen before. So we wanted to see whether this foundation model paradigm, where someone has gone and trained a giant model on something that has nothing to do with the Lorentz attractor, whether we could use that sort of large foundation model paradigm to predict chaotic systems and do any better than we would expect by random chance. So what we did is we took a foundation model. We don't have nearly enough compute to train this ourselves, so we took one that was trained by Amazon that was designed to predict effectively sort of a supply chain forecast. And this is trained on a whole bunch of data that has nothing to do with our problem, but we tested on the same test partition that we use for all of our forecasting benchmark. And one of the things that popped out when we did that is that the foundation model actually does surprisingly well on this forecasting problem. So on the left here, I have the true dynamics that you would expect to see if you got a perfect forecast. On the top, I have traditionally trained models where they saw a bunch of time points from this chaotic system, and we just asked them to predict new time points. And you can see that the same models that did well on our benchmarks are the ones that sort of get the attractor most right. But if you look at this large-scale foundation model, it actually does better than you might expect, right? So this is a model that has never seen the Lorentz attractor before. It's just a very large model that was trained on a whole bunch of time series, but it sees a whole bunch of points from the Lorentz attractor purely as a context or like a prompt that goes into the model. And one of the things that we found is that it appears that the larger models, as the scale gets larger and larger, so you can see that the largest model here is close to 1 billion parameters, they actually gradually improve in their ability to reconstruct the underlying attractor. So this is interesting. On a sort of simple level, we think that this suggests that there's some pure advantage from scale, but we think there's a few other things going on here. Like, we think that there's some aspect of in-context learning where during the observing the context is learning something about the measure of the attractor. So we have a little bit more to say about this, but for now I see this as just an advertisement that scale alone can give you an advantage in forecasting, even if you don't necessarily train on the underlying system. So this is something that we thought was pretty interesting because it suggests that, as models get larger, they are getting an advantage on this problem, and that maybe suggests why we're able to forecast several Lyapunov times further than was thought possible even a decade ago. But it still doesn't answer, I think, the simpler question, which is, given that these models are predicting further than was possible in the past, and given that there's been a lot of work on forecasting chaotic systems even before sort of the advent of these larger models, the question is, what is it specifically that these models are learning that somehow wasn't picked up on before? What are these models conceiving of in the underlying dynamics that's allowing them to build forecasts that are somehow more effective than what was seen before? So we wanted to see if we could probe and see something a little bit more systematic about what's making it possible for these large models to generate forecasts, what they're specifically learning about the underlying system. So we wanted to poke around and see what these models found that physicists hadn't noticed before. Okay, so to motivate what we're going to see, I'm going to show a video that just shows the process of going through and training a couple of these models that did pretty well in this benchmark. And the way I'm doing this is that all of these models are trained iteratively. So at every point in their training, I can just look at what their forecast is, and so I can see the process of their forecast improving as they see more training data. And what I want to emphasize, and I'll mention that I'm spacing logarithmically, so we see the early time points of training a little bit more finely than we see the later points. That's why it gets a little bit crazy. What I want to emphasize that we see here is that early on during training, a lot of these models do what you might expect, which is that they just focus on getting the next couple of time points right. See this very clear sort of local trend where they just try to continue what they've already seen. But then as you go further and further into training, you see something that almost looks like a discontinuity, where they go from just getting the first couple of time points right to really trying to capture the whole global geometry of the attractor. And you can see this, I think, most strikingly in the transformer example, where at some point during training, it goes from just sort of continuing the loop to trying to capture this whole sort of figure eight. And this suggested to us that maybe generalization and generating long-term forecasts really has something to do with whether these models are able to couple into the underlying sort of geometry or the invariant properties of the dynamical system that they're learning. So we wanted to probe to see if maybe we could peel out what specifically about the underlying properties of the dynamical system these models suddenly learn when they are able to generate these long-term forecasts. So it turns out if you dig a little bit deep into the nonlinear dynamics theory, there's actually a pretty principled way to think about the idea of how you deconstruct a dynamical system into its parts. And I won't go into the whole nitty-gritty on this because it's a whole field. But the idea is relatively simple, which is that if I have any dynamical system that's ergodic and satisfies certain properties, that system is usually dense with invariant solutions of the underlying dynamical equations. So in a low-dimensional system like the Lorentz attractor, the invariant solutions are essentially just orbits. And so I can always think of the attractor of a system as something like the union of a large number of these invariant solutions of the dynamics. The nice thing about these invariant solutions is that they aren't true solutions in the sense that they're not stable. So the dynamics might get stuck near them, sort of in a metastable sense, but they'll never actually get stuck in a solution forever. However, because they're invariant solutions, the dynamics can linger near them for very long amounts of time. And so you can always think about any sort of nonlinear system as sort of a series of visits among characteristic invariant solutions that jointly give rise to the underlying attractor. So this is an interesting idea because it suggests that if I wanted to break apart some fractal object like the Lorentz attractor, rather than just thinking of it as a series of points, I can really think of it as a set of these invariant solutions that jointly dominate the underlying measure. And you can even take this idea further and even write down a whole probabilistic picture of the dynamics in terms of these solutions. So this picture is kind of suggestive to us because it's just that rather than thinking about just trying to approximate each point in an attractor, maybe what really matters over long timescales is whether you're able to couple into these underlying invariant solutions that dominate the measure over long time points. And I emphasize that I think that this is a really suggestive idea Because on some level, this allows us to connect the way that we think about dynamics, which are, let's say, deterministic here, and which have this underlying sort of complex attractor, to the way that we think about modeling really complicated probability distributions, which is what a lot of these newer models are very good at. And so in the same way that if I have some really sort of complicated probability distribution, I might approximate it by trying to get the most dominant modes from it first. Likewise, if I have a really complicated attractor, maybe what I really care about is trying to capture the dominant invariant solutions that take up most of the measure. So we have this loose view that you can almost think about the invariant solutions as sort of dominating the other underlying measure. And so if a forecast model can pick up on the ones that are the most stable or which kind of take up the most time in the dynamics, the model might be able to succeed more than a model that isn't able to pick up on this structure. So we have this sort of pocket intuition then that whether you're able to forecast a model really comes to, or whether you're able to forecast a system, comes down to whether you can pick up on these unstable invariant solutions of the dynamics. Okay, so that's the idea of invariant decomposition of dynamical systems. So we wanted to see if we could take this picture that different dynamical systems have these different invariant solutions and they dominate whether you can predict them or not, and compare them to our original forecast results to see if they tell us which of those models will do well or not. So if you go through all of these different 135 systems that we were generating forecasts on, you can analytically compute these different invariant solutions. We have a couple of tricks we devised for doing this quickly. And it turns out that across all of these different dynamical systems, there's actually pretty high heterogeneity regarding how many of these orbits you have to capture in order to capture the majority of the measure of the underlying attractor. So some of the systems have relatively simple solution structure. They have like a couple of orbits that capture most of what they do, whereas other systems require a lot more orbits. And you can almost think of it as how many modes do you need to approximate a probability distribution. Here's just how many orbits do you need to capture the underlying attractor. So we have this loose intuition that some of these systems should be harder to learn because they require more orbits to approximate their underlying attractor. So for every one of these different systems, we can extract something like a measure of how many orbits you need that should give an estimate of how predictable the system is or not. So we have that number for all of these different 135 systems. So what we're going to do is we're going to correlate the performance of the forecast model with how many of those orbits the underlying system took. So this is going to be a correlation across these 135 systems. And one of the things that we start to notice is that whether or not a system is predictable over very short timescales more or less comes down to a Sliopinov exponent, which is an idea that most people in forecasting wouldn't find that surprising. But over the really long timescales, the sorts of timescales where you really are trying to get the broader shape of the attractor, whether or not these models are able to predict the system really comes down to how complicated the orbit structure is. So in other words, whether a forecast model succeeds or not on these 135 systems really depends on whether the model is able to capture the invariant orbit structure of that set. And as the models get bigger, we see this loose effect where the models are better able to capture more orbits, suggesting they can account for geometry a little bit better. So this is our toy model of how sort of prediction works, which is that over short timescales, you sort of continue what you saw before, but over long timescales, you really need to be able to pick up on the sort of underlying modes that dominate your training data set. Okay, so then we wanted to bring this back to sort of how is this relevant to the broader questions here, right? So here we're doing a lot of sort of like toy problems that are more or less sort of like low-dimensional chaotic systems, but a lot of the other folks at this conference are maybe thinking about systems that are much higher dimensional and much harder. So in the context of the sort of things that other folks think about, sort of higher dimensional systems, one question would be, how do we expect some of these results on these low-dimensional systems to inform whether we can predict things like PDEs or fluid flows? That should be much harder. One idea that we have is that this picture that invariant solutions matters should hold up even when we move to higher dimensions. So for those of you who work on things like fluid flows or sort of sedimentation models that involve many coupled variables, there are generalizations of this orbit picture that exist for higher dimensional flows. For example, in fluid dynamics, there's a lot of focus on coherent structures as a coarse-grained way of thinking about high dimensional dynamics. So we think that probably this picture of low dimensional invariant solutions holds up, with the caveat that finding these higher dimensional coherent structures could be a bit harder. One thing that we do think is going to be different when you go to higher dimensions that might complicate this forecasting picture is that a lot of the work that we're showing on these low-dimensional chaotic systems makes some implicit assumption that the dynamics are stationary or that they're ergodic. But generically, it's the case that in high-dimensional dynamical systems, you usually spend a lot of time on transients, where you get stuck in regions of phase space that you'll never visit again. And this is a generic mechanism. It's well studied in things like turbulence, where if you have a very high dimensional system, you can get stuck near saddle points for very long amounts of time, which means that this idea that you're approximating some measure doesn't necessarily hold. So one complication that we think we have with our picture of forecasting is that when you go to high dimensions, you have to have a specific model that can account for whether you have events that you don't see before. And we think that this generalization picture might complicate the ability to build long-term forecasts. Okay, so I'll go ahead and wrap up there, and I'd be happy to take any questions. Thank you.
Any questions?
Thanks for a great talk. I just have a question to these periodic orbits. So you have many of these unstable orbits in these chaotic systems, but they are shadows of lower order. I mean, so it doesn't seem to me that you really resolve, because it requires high precision to determine orbits that are just more than a period 1 or period 2 orbit. Because take a period 5 that could be almost existing, but be a mirror or shadow of the period 2 and 3 orbits. So you kind of end up in the lack of predictability, which is the same with the Lyapunov exponent, that it's hard to predict when you cannot determine exactly these orbits.
So at least in low dimensions, a lot of the times the higher periodic orbits, they themselves are shadows of lower period orbits. And so if I say that I'm going to have a series approximation of my attractor in terms of these orbits, if I say that I'm going to truncate that at some length, then I can sort of effectively just rescale the weights of the lower period orbits to account for that. So even if I'm truncating this approximation of the dynamics with a couple of these invariant solutions, because if I capture the low period ones, I get aspects of the high period ones, I still have sort of a probabilistic description.
What is your measure of how, so you said a few times that you have models which capture, past a certain Lyapunov time. Like, what is your measure of actually being able to forecast the system past it? Is this like a probabilistic measure that you're looking at how well you capture the invariant, like the invariant measure of the problem, or are you actually looking at just trajectory predictions?
So for when I talk about specifically like how many Lyapunov times, for that I'm using just a pointwise measure. So I'm saying that some measure like you could use mean squared error, but there's other errors that people use that are just pointwise. Was this point that it predicted close to the true point? So we can use that to back out like a time scale, which is like at what time scale does the error exceed some tolerance, and that we can get that to say that it's this many Lyapunov times. But we do also measure directly whether the attractor looks right by measuring the fractal dimension, and we can see whether the fractal dimension matches. Yeah.
Okay.
But we don't use that to get this number for how long we predicted. We just use that to measure the quality of the forecast.
So it's not like, I mean, you could also imagine using a probabilistic metric, like the Wasserstein distance, for example, or something where you can compute, between two measures.
So in the zero-shot paper, we did try using the KL divergence, where we basically center like a Gaussian at each point in the prediction, as well as in the true trajectory. So you sort of have a Gaussian mixture, and you find the KL divergence between those two. It ends up being pretty similar to the fractal dimension, because it's kind of doing the same thing in that it's measuring sort of spacing among points, whether it's similar across the true and the predicted.
And I did have a question also about that. So what is your input to the transformer? So I imagine the transformer is the foundation model that you took from Amazon, right? Okay. Mm-hmm. So what is the input like in this zero-shot case?
Yeah. So this is one thing we were going back and forth on, is whether it counts as zero-shot or few-shot, because the input is, let's say, 512 time points from the attractor, but it's not training on them. It's doing some in-context processing.
I see.
Yeah.
Okay, so you give it a small snapshot of the trajectory, and then you let it go out further.
Yeah, although, I mean, so in our case, like, we're using a time resolution where that's still several Lyapunov times, so it is enough to get a probabilistic view. So that's why we're wondering if it's learning some probability distribution in context, because it's seeing so much of the attractor. Yeah.
Thank you.
So when you talked earlier in your talk about, When you talked earlier in your talk about the calculating like all of these different invariant measures, do you see a correlation structure between all of the different invariant measures between each other? And could that produce some kind of like explanation as to why there may be some missing space in the near space around your UMAP picture, basically.
Yeah, so this is something we've been trying to piece apart, which is that when we do this calculation of how many orbits do you need to capture most of the variance, generally a lot of these systems require relatively few, and so somehow a lot of models that people have published have relatively few dominant orbits. But generically, if I was trying to just build a complex system, I could always just pick how many orbits I want. I could have like tori that are each have their own dimension that they exist in. And so we're wondering if there's some reason why models that people build typically have a few spanning directions. We think there's some literature on like model space and biology that has talked about this. So we're not sure if there's if that's either a bias in what people publish or if it's a bias in what people choose to, like how people choose to model their systems. But I agree that it's a little bit weird that a lot of these systems have sort of a decaying orbit structure. Yeah.
So I was curious, you mentioned that it makes sense that for a larger model like transformer, because when you have more training parameters, you can parameterize the nonlinear PDE to something that's more linear. And I was wondering, is there formal analysis to suggest whether 10 to the power of 6 is the right number of parameters for a particular system?
Yeah, so one of the pros we play around with is that both in the zero-shot case, but also just when we train a large model traditionally, is we look at whether in weight space we can train some sort of linear probe to predict the dynamics and how much we lose in the predictability there. That's part of where this sort of loose Koopman claim comes from, is this idea that you can take apart the model post-training and see how linear the dynamics are by sort of fitting a secondary model in that space. And I wouldn't say we have like a specific number per se per system, or I'm not sure I believe any specific number we have, but we can at least quantify that it appears linear.
I have one more question. So in moving all this stuff to a higher dimensional space, hoping it linearizes it, that reminds me, maybe it's completely unrelated, but this is what I think like the Lime explainable model tries to do, and it says that there's some, in the very near space of a single prediction, everything's basically a linear relationship. So let's try to use that to explain how this particular prediction was made for this particular point. So not the entire time series, but this point in the time series. Or in the case of Lime, that's also true for like predicting which pixel in a picture is used to say it's a cat or a dog or something. But
So I'm not familiar with that interpretability probe, but would it be linear in nearby time points or linear in?
yeah, I haven't seen it applied to time series data. I've only seen the examples applied to like photos and stuff like that. But it is basically the idea is that you can just approximate what the model knows with a linear model.
Yeah, because I mean that is something that, so back in like the 90s when a lot of early stuff on sort of forecasting chaotic systems was done, that was one of the big ideas from like sort of Sugihara and his era, was that if a model is purely sort of like you're forecasting, let's say, a linear system with noise versus a nonlinear system, one way you can differentiate that is whether if you build your forecast model, you need to weigh nearby points just linearly or whether you need to have some penalty for distance, and the latter ends up being a diagnostic for whether it's a deterministic system rather than just being a chaotic system or a linear system with noise. And so there is some conceptual idea there that you could actually use whether you need to use a linear model as a diagnostic of the type of dynamics there. We haven't thought that much deeply about that, but there is there is some historical connection there to some earlier stuff.
Okay, cool. Maybe we should cut because now we have a coffee break and people can continue talking with William. So let's say thank you to William.
Thanks.